Suppose you want to minimize the sum of two convex functions, neither of which is differentiable. One robust approach is to use Douglas Rachford splitting. Let's walk through how it works. First, the problem we aim to solve consists of finding the minimizer of f of x plus g of x. To be precise, we assume both functions f and g are closed, convex, and proper. This is the fancy jargon for saying that they are nicely behaved. Importantly, these properties hold for a lot of problems we encounter in the wild. And it means the functions do not need to be smooth. For example, they can represent hard constraints, as we will see in our toy problem. Next, we assume both the function f and the function g are proximable. That is, we can easily compute the proximal operator for each function. The proximal operator definition is shown here, and you can watch my other video on proximal operators for further background. With Douglas Rachford splitting, what we do is create three sequences using some initial point z1 and step size alpha. We start by first applying the proximal for f to z1 to get x1. We then apply the proximal for g to 2 times x1 minus z1. Then we update z by adding our value for y1 minus x1. This process is then repeated over and over to generate successive solution estimates xk and yk. Importantly, both xk and yk converge to a minimizer x star for any choice of step size alpha. The sequence zk also converges, and its limit is a point for which taking the proximal for f gives the minimizer x star. Now that we know how to compute updates and that they converge to a solution, let's turn our attention to a toy problem. Suppose I am working in the Euclidean plane and want to minimize the L1 norm subject to a linear constraint. I can rewrite this as the sum of f of x plus g of x, where f of x is 0 if the constraint is satisfied and infinity elsewhere. We call this an indicator function. Then I can let g be the L1 norm, which in this case is precisely the sum of the absolute value of x1 and the absolute value of x2. Notice the yellow line where the constraint is satisfied, and the pink lines where the level curves of the function g of x are shown. The minimizer x star is at the point 3/2, 0. Now, as we mentioned earlier, to execute Douglas Rachford, we start with an initial guess z1, which is here shown by a dot. Then I compute the proximal for f to get x1, which is precisely the projection onto the L line and is here shown by a green dot. Then the proximal for g is a soft threshold operation, which results in the orange dot shown for y1. The update z1 is the difference between y1 and x1, as shown by the white line. Now repeating this process over and over, we can see the convergence of all three sequences. Note, each xk is feasible, meaning it satisfies the linear constraint, which is not the case for yk, which only obtains feasibility asymptotically. The behavior of xk and yk can at times appear oscillatory. However, a neat property of the sequence zk is that the distance between each point and its limit is non-increasing. In other words, zk will settle down in a nice way, and as it does, so also will xk and yk. Sure enough, we can see that the sequences xk and yk converge to the minimizer x star. That's all for now. If you enjoyed this video, please make sure to like and subscribe. Thanks.